In the previous lecture, I talked about a ground change in our methods of communication that allowed larger and larger amounts of knowledge to be traded faster and faster due to improved printing processes that allowed inexpensive, high-quality images to be widely distributed. Now I'm going to talk about an image replicating technology, blueprinting, that emerged at the end of the 19th century using Lukens Steel as an example. Drawing was an integral part of the design and manufacture process. Mechanical and architectural drawings were essential to the design and construction of nearly every machine, as well as the design and construction of the plant. Drawings became the work orders for new machinery and buildings, and they were also the archive from which repairs were made. On the left is an older drawing done on drafting linen, a smooth cloth that was translucent. This type of drawing was gradually replaced with blueprints, which were easier to replicate, on the right. In an 1884 American Society of Mechanical Engineers Transactions, Charles T. Porter wrote, quote, "The introduction of the blueprinting process has quite revolutionized the drawing office." Then he gives more detail. "Our drawings are studies left in pencil. When we can find nothing more to alter, tracings are made on cloth. These become our originals and are kept in a fireproof vault. Our working copies are blueprints." This was the process then. All of the drawings prior to 1900 made by Lukens Steel were done on the high-quality drafting linen. Drafting linen resembles oilcloth. It's strong with a smooth surface and partially translucent. The mechanical artist either traced previous iterations or used draftsman's tools to make new ones. This drawing is a specification for dies, two-piece molds into which sheet metal was pressed to form the handles for circular covers for boilers called manheads. These earlier images were usually named and dated in the lower right-hand corner with a numbering system for the drawings stenciled below. Later, this information would be systematized. As can be seen from this detail, there was often further writing in pen or pencil on the drawings. The drawings were used and modified continually. As machines gained complexity, it was necessary to show more detail. This is one of several drawings from 1912 that were specifications for a flanging machine designed at Lukens Steel to make bent edges for the circular manheads. By this time they adopted a more conventional naming system, as can be seen in the lower right-hand corner. Making drawings was a necessary part of the design process. As Eugene Ferguson notes, quote, "When the designers think they understand the problem, they make tentative layouts and drawings, analyze their tentative designs for adequacy of performance, strength, safety, and then complete a set of drawings. The finished drawings and specifications become the formal instructions to guide their work." End quote. In some companies, engineers made drawings that would then be mounted on cardboard and clamped in place in front of the machinists as they worked. This is the naming system that Lukens Steel had developed for the later pen and ink tracings. Each drawing was important because it contained the plans to reconstruct a piece of machinery if it broke down. They were all cataloged in a drawing index that I'll describe later. When Lukens planned a new office in 1913, they used a reverse blueprint process to duplicate their architectural drawings. As can be seen from this image, they were not experts yet. Overall, the paper used in blueprinting was much more brittle than the drafting linen. This is another sheet from the architectural blueprint set for the new office. It shows the location for the drain for the steam heat. Every detail had to be specified before being handed over to the men who would do the construction. Lukens saved many of their drawings, both the ones that they created in-house and also incoming drawings from other companies. In them we can see a wide array of types of drawing reproduction used in the late 19th and early 20th centuries. This is one sheet of an incoming specification for a steamboat boiler from 1899. As you can see, the paper has been damaged over time and there's no formal naming no formal naming system in the lower right-hand corner. This is a detail from a larger blueprint, also one of a set, that specified how to build furnaces for fire brick stoves. This type of detail was necessary to show the complexity of the machinery. This was how one company was able to tell another, remotely, how to make parts and systems. This blueprint is from 1897 and, like the last, had no standardized naming system. The set also included several handwritten pages along with the drawings that gave further instructions on how to build the stoves. This is a 1920 blueprint from a subcontractor of the Pennsylvania Railroad showing the steel shapes necessary to make a locomotive firebox. Most specifications for complex machinery required multiple sheets. Since this blueprint is from a later date, there is a formalized naming system in the lower right-hand corner. Eventually, each company developed its own standardized naming system to keep track of their prints. It usually included a section for listing revisions and a section to provide the name of who had traced, drawn, examined, approved, and issued each image, as well as the name, scale, and date. Sometimes these slots were used and sometimes they were not. Lukens had perfected their blueprinting techniques by 1916. This brought them into line with common custom. This is the naming format that they used. They made blueprints not only for machines, but to draw detailed layouts of each plant. Their blueprints were frequently revised. Sometimes they were drawn on with colored ink, and sometimes new sections were pasted on. Eventually, every mill had a schematic representation of the interconnected industrial processes. This is a tiny detail from a much larger drawing. Unfortunately, it's almost impossible to photograph and display these large blueprints, which are kept in a separate section of the Hagley. They also created blueprints of the entire plant layout. This one was made to focus on the railroad tracks coming and going from the plant site. It's difficult to photograph these plans because of their size. This is an example of a sepia print, done in brown instead of blue. It's part of the plan that Charles Lukens Houston made collaboratively with United Engineering Foundry for the new 204-inch mill, which would become the largest in the world. John Brown wrote, "Novel designs generally originated with an oral description or a written specification from a customer. A lead draftsman designer then translated this original concept into a rough sketch. Fundamental to the innovative process, such sketches often passed through many iterations as all came to agree on the ideal combination of design elements, parts, and proportions." End quote. This sepia print represents an end part of the planning process that resulted in this. Lukens called it the big mill. There were hundreds of drawings, and they were extremely important to the operation, used and revised frequently. In most manufacturing plants, they numbered them, organized them in flat drawers about 2 inches deep, and kept an index in order to be able to locate them. At the Lukens plant, they kept this index until 1915. Since the previous image didn't give a sense of the size of the book, I'm showing it here. It was well used. The cover had worn off, and nearly every page was marked with dirty fingerprints. It was difficult to organize the images. The organization of the index was never entirely satisfactory, and it was never complete. It was separated into alphabetical sections, each letter representing one part of the plant, one system in the plant, or one type of structure in the plant. These categories include gas producers, which were then subdivided into old plant, universal mill, slab mill, not in use, foreign, etc. The drawings were numbered roughly sequentially, with space left in between for further revisions. If there was no number available for a new drawing, they sometimes appended a letter to the number. Many of the pages were scripted by a single hand, especially at the beginning, But over time, additions and deletions were made by many other hands, mixing the ornate clerk's script with printed letters, cross-out scrawls, and even shorthand, as seen here. In 1915, they discontinued using this drawing index, but kindly saved it with some of the drawings for me to study almost 100 years later. This is one of the schematic layouts of the plant. The creation and maintenance of the plant would not have been possible without these drawings. Communication by drawing was integral to the industrial process. If you look closely, you can see that there was an office, a blueprint room, and a drawing room. Both the blueprint room and the drawing room are larger than the office. That can give you an idea of how important repeatable images were to creating the world that we live in today. In 19th and 20th century engineering, drawing was an essential part of technical communication. It was regularly taught in engineering programs. It was required in the sophomore and junior years at West Point in 1832, and combined with descriptive geometry, it made up 32% of the required curriculum for the mechanical engineering degree at MIT in 1867. Here are some sources for further information. Details on the blueprinting and sepia printing processes, including their reverses, are hard to come by and often only known today by archivists working with these documents from the past.